This is our third lesson for our unit on waves, and in this lesson we're going to take a look at something called standing waves, something that's really actually important for musical instruments. Before we get right into the nuts and bolts of how standing waves work, we're just going to take a look at one topic that we're going to need to know about in order to look at standing waves, and that's something called interference. And it's something that can happen when you have two or more wave sources. We're just going to have two for the ones that I'm going to look at here. And you've got this picture in your notes. It looks something like this. And these are supposed to be sound waves perhaps coming off of a couple of speakers, or maybe some ripples in a pond coming from two sources where people are taking their fingers and making little ripples come away from the shore. Let's actually kind of back things up a little bit and just maybe watch one speaker as it goes and sends out little push-pull waves of sound into the air. So source number one could be radiating out some waves like this, and they're heading out into some room. But while source number one is doing that, source number two could be sending out that exact same wave sound like this. And those waves are going to start to overlap each other in this region here. And as they do overlap, you get some very, very interesting patterns depending on where you're standing in the room. So here's a little animation of that turned on its side, where we've got some wave source here that's actually sending out some ripples, and here's another one that's also sending out some ripples. And where it's interesting is when these waves start to overlap with each other, where they start to have some superposition. And there are some places in space, like this whole band here, where when the waves arrive, they actually arrive together at the same time in phase. And it really causes a reinforcement, causes a real increase in amplitude for that sound signal. But then there are other places, like all along here, where it just stays light green, where the waves, when they arrive, and they are arriving, right? They're coming from these speakers. But when they arrive out of phase, where one speaker is trying to do one thing, maybe push the air at you, and the other one is trying to pull the air away. And all along here, it continually does that as those speakers continue to send out that same tone that they're generating. And so we get these places where things interfere really well, and you get large waves, and then we get places where they interfere destructively, and we hear no sound signal at all. Or if this was a little pond with some ripples on it, you'd actually see no ripples there at all. Now let's go and just take a look and see what kind of notes we can add in there for that. Any places where you've got the crests lining up with the crests, and I'm going to assume that that's where the solid lines, the solid blue and the solid green are happening, where those are lining up together, you're going to get loud constructive interference. And you might think, well, that's only down the center line, and certainly that's one place where it could happen. But it could also happen here, or here, or here, because the waves would be arriving together in phase. And then we've got other places where a crest, perhaps like I've drawn here with the green solid line, lines up with a trough on the blue set. And in that position, all day long, not just at this moment, but all day long, you're going to find that you have this destructive interference where things are nice and quiet and you can't hear any sound at all. And this issue of interference between multiple sources of waves is going to be important for when we start to look at standing waves. So let's go here now and take a look at how standing waves work. Key things that cause standing waves, you have to have happening at the same time interference, which we've just talked about, where you have constructive or destructive interference perhaps, and reflections off of some sort of end. So these waves can turn around and come right back at you and do that interference all over again. And I've got actually a couple of little breakdowns of a standing wave that's about to happen here. And on this side of the page, I just want to take a look at the issue of interference. I want you to imagine that these little wave pulses are heading towards each other like this. So we can draw some little velocity arrows here showing which way they're going. And when they get together in the middle, it is going to be really, really serious there. We're going to see this massive big pulse right there in the center because of that constructive interference where both pulses are trying to go up at the same time. But now imagine these pulses have passed through each other and they're continuing on their way towards the walls. And I want to imagine for a moment that these are going to be some nice rigid walls, like the end of a guitar where you have the bridge or the nut. And you've got this little slinky wave, this guitar string wave, or actually set of waves that are about to hit those edges that are nice and rigid. So this pulse is still going out, and this pulse is still going out. They're going to have a reflection off those ends because the energy has to go somewhere. And if it's a nice fixed end like this, then they're going to come back inverted. They're going to come back upside down. But they're going to come back at each other again. And just like they made a big amplitude on the way by in the first time when they were here, when they come back, they're going to make a big amplitude there again. And that's what standing waves are all about, just getting your timing right so that if you have these multiple little wavelets, if we want to call them, bouncing around, there could be places on the string in your environment, in your medium, where you have this awesome interference. But you might also have places where you have destructive interference, where they fight each other. So let's just take a look at this little page here that I made, just so that we can kind of look and see exactly how a standing wave might be forming. I've got two different standing waves slowly being formed here. Over on the left-hand side, it's kind of the simplest possible one, is what we might call the fundamental. And there are a couple of little pulses that are happening here. One's coming along like this. Actually, let me just fix my computer here for just a second. Okay, I think I got it working here now. So we could have pulses that are heading towards each other like this. They're on a collision course, so to speak. Not that they collide, they just interfere when they get there. They superimpose. And then we have this really big amplitude that's going to happen briefly. But then those pulses keep on going. They keep passing on their way, and they're going to eventually get to the edge. And then when they get to the edge, if it's a nice fixed edge, they're going to turn around and they're going to come back. And on their way back, they're going to be ready to interfere again. But this time, this big pulse goes down. And those pulses will keep on going. They're going to bounce off the edges again, and then it'll look much like the upper picture. And that particular story is what we call the fundamental. It's kind of the simplest possible frequency that this can happen at. But if we're willing to have maybe like 4 little pulses travel around, you can get this sort of thing happening. Hey, maybe this one's going this way, that one's going that way. And you can see that right here, they're going to make something really big. But at the same time, maybe I've got a couple of pulses over here that are going to interfere, superimpose on each other, and make something really big there. But then they keep going on their way, right? This pulse keeps on going. It's going to get to the wall. This one's going towards the center. This one's going towards the center, and that one's going towards the wall. Now, this one, when it hits the wall, it's going to turn around and come back. There it is, starting to come back. And this one, when it gets to the wall, it's going to turn around and come back. Yep. Here it is, coming back on the upper side now. But these two are interesting. These two here, they're actually going to superimpose with each other. I'm just going to say collide. They're going to go on top of each other, and they're going to cancel each other out. We're going to get some destructive interference, and that very center of this guitar string isn't actually going to go up and down at all. And so we have one section of the guitar string where we're going to see really big swings. Those are actually called antinodes. Another spot right there. And then there's this spot here that's actually called a node. Technically, the ends are nodes too. Nodes are places where you don't see the string moving around at all. And that's the idea of standing waves. It's actually a combination of interference, both good and bad, happening when you have these waves that are reflecting off of the ends all day long, over and over and over. So with that idea in mind, let's take a look and see how some musical instruments work. We're going to start off with guitars that are fixed on the ends. So for standing waves, we're going to look in Physics 11 at 3 different cases, and we are going to start off with that guitar case. Before we do that, I want to show you some just animations that I made to try to show you what these pictures are all about. So let's take a look at a couple more. So this one here, here's what I tried to show you happening. The blue is actually the guitar string, and on that guitar string there are a couple of little wavelets, little pulses that are passing around, 2 of them in fact, and they're bouncing off the ends, flipping upside down, and then going back by the middle. Just for clarity, just to try to help you see this, above and below the blue string, those red ones, those show waves that are just going in one direction. So the upper red guitar string there is showing you any pulses that happen to be currently traveling to the left. And the pulses are really on the blue one, but if there are any on the blue that are traveling left, you get to see them on the upper part. And the lower red one just shows any pulses that are currently traveling to the right. So you can actually kind of follow one of those blue pulses. I'm going to start off with one over here on this side, okay, and we'll go right now. So there it is, going to the left, and it bounces off the wall and goes back to the right, bounces off the wall, goes back to the left, and it keeps doing that. But when it meets up with its partner, right in the middle, you're actually seeing this big, huge amplitude happen. Now, the actual guitar string isn't so crisp. It doesn't have little triangles like that bouncing around. So let me kind of just widen them out, and you can start to see this standing wave form. But the idea of how the standing wave happens is right here. Reflections off the end, and then constructive or destructive interference in different places. Reflections off the end, and then interference. So let's broaden these peaks out a little bit. This is the same simulation. I just ran it again with slightly broader peaks. That's all I did. And take a look at that blue guitar string. You can start to see it do this kind of classical standing wave. All I have to do is just broaden them out a little bit more. So I'm just taking these little wave pulses and I'm doing nothing but making them wider, not even making them any taller. And here we go, nice and wide. They would look like this. And when I say they, I mean, yeah, there are two of them. There are two pulses right now, bouncing off the ends and then interfering with each other when they go by. Whenever they go by the middle, they work together to make the string go up or make the string go down. And then they're bouncing off the ends and then coming back to do that same thing over and over again. This particular motion on the guitar string is called the fundamental or first harmonic. It's the simplest, lowest frequency that you can get a guitar string to bounce around at. But just like that picture we had in our notes back here, the diagrams that are over on the right are actually showing something called the second harmonic. And that's when the picture might look a little bit more interesting. It might actually look like this. So this is what happens when four little pulses bounce around. They're bouncing off the edges, and whenever they go by the middle here, they're actually canceling out. That's why this doesn't shake at all. But look what happens when they go by this spot 1/4 the way along the string. They're making it bounce like crazy because we have constructive interference there. Also at 3/4 the way along the string, there's definitely some good, healthy, constructive interference going on. But we do have destructive interference at that node right in the middle. And we've got those nodes right at the end of the story. And you can play this game all day long. This is the second harmonic. If you put a couple more pulses in there, you can get this frequency, the third harmonic. And these are called standing waves because they appear to be doing their wave deal, but standing in place. You know, we talked so much on the first day about how waves have to be moving across the room, and you have to have this spatial variation. Well, this is doing that, but it's just two of them that are doing it at the same time, or in this case, actually 6. And it creates this illusion of a wave that doesn't move left or doesn't move right. It just seems to hover in place, but it still has an amplitude. You know, we can look at it and go, okay, how tall does this go? You know, there's my amplitude. And there's even a wavelength, right? The wavelength for this story could begin at 0 and could end right around here, about 2/3 the way along this little graphic that we've got. And there's a frequency and a period, and that's what we're going to look at in our notes here. So filling in some of our blanks, let's look at the guitar string. Let's say that your guitar is some length called L. So this is from the bridge to the nut in the guitar. That's the edges where you hold the string, and we're going to hold them tight and watch some little wave pulses bounce around on the inside. And so you have this table, and the first harmonic looks like this. The N in this graphic stands for node, meaning it's not moving at all. And AN is antinode, where it's bouncing around a lot. Now, back in the graphic, if I can make that happen here again, if I can get there. Maybe there it is. Oh, let's go back a bit. That was this one. At a moment where I might freeze the picture, like right there, I can see a crest but no trough. So this is not a full wavelength that we get to see. The guitar only has half a wavelength at any one moment. So the wavelength for the actual frequency would be 2 guitars long, or actually 2 L's long. And so in this box here for wavelength, I'm going to say, yeah, the wavelength for the standing wave is twice the length of the instrument. Okay, the frequency. How do you find out what frequency this note will be? Well, we do know a way. A couple of days ago, we found a way to find the velocity of the wave in a guitar string. It was a little technical. It had a square root and tension and like a linear density, but we can find the velocity. And we now have the wavelength. So we can go to the wave equation, V equals lambda f, and we can start trying to figure out the frequency. Now, just before I get there, I'm going to show you a sneaky little way to remember the wavelengths that are going to show up for all these different harmonics. So sure, this is only half of a wave long, so the actual wave is 2 guitar lengths long, 2 L's. But a neat way to remember that is going to be 2 over 1 times L. And you might look at that and go, why would you want to call that 2 over 1 times L? Well, a little cool pattern starts to develop here in a minute. Okay, frequency. Just using our equation, all I'm doing is using the idea that B is equal to lambda F, and I'm just rearranging that for F, trying to find frequency. So it would be the velocity of the wave. Now remember, we did come up with a cool little equation that works fine for guitar strings. But we can take that velocity, divide by the wavelength, and find the frequency. And the wavelength apparently is 2L, right? A couple of guitar lengths long. And so that'll be our frequency. Now, a neat way to remember this is going to be 1 times V all over 2L. And you might look at it again and go, why would you put a 1 in there? You're just making a mess of it. It's going to help you out here in a minute. So that's going to be the lowest possible frequency that you can play on that guitar string. Sometimes music and physics people call that F with a little 0, F naught. This is the lowest note. This is the first harmonic, and it is often called the fundamental, meaning that's where it begins, right? That is the lowest note that hides in that guitar string with that tension and that length. But it's not the only note that you can play on that guitar string. It is possible to play a note like this. Right? If you actually put your finger just gently right here while you pluck the string maybe around there, you'll actually get this note coming out. It's got a totally different frequency to it. So this is the second harmonic. It has like a double wiggle with another node there in the middle, and it'll appear to stand in place. And so if you ask yourself, well, how long is the wavelength for the standing wave? Well, if you take a look at it, you can catch just the right moment. Like, just take a look right, I like to look right now. There, full wave. The guitar itself is perfectly 1 wavelength long. So lambda, the wavelength, corresponds exactly to the length of the guitar. And so we can put in here that lambda equals L, or another way to remember this, 2 over 2L. And you can start to see the pattern here, right? This is the second harmonic. This one was the first harmonic, second harmonic, and it's got a wavelength of 2 over 2L. Now if I go and put 2 over 2L in for lambda over here, I can find the frequency. And what ends up happening is I end up with just V over L. And it's actually a really useful thing to ask yourself, for this second frequency that you can have, how does it compare to the first? How does it relate back to the fundamental? This one was V over 2L, and this one's just V over L. Well, another way to think of V over L is 2V over 2L. And you can see some consistencies here, right? V over 2L, V over 2L, but now we've picked up this extra 2. And that tells me that mathematically, this frequency will be exactly double the first frequency, which in the world of music is actually 1 octave up. It'll be like the same note, but an octave higher. Well, you can keep going. You can do those higher harmonics. Here's the next one, the third harmonic. It has another node in the center, so it ends up with 3 little bumps on the guitar string if you catch it at just the right moment. And that would look like, I can get it to go to it. Oops, yeah, like that. So there's the third harmonic. The actual guitar string is more than a wavelength long. You know, 1 wavelength would be right to there, just 2/3 of the way along the string. And this is going to have a higher frequency to it. So the numbers for this one. The wavelength for the standing wave is 2/3 of the guitar long. Okay, so it's 2 over 3 times L. So we have 2 over 1 times L, 2 over 2 times L, 2 over 3 times L. And if we now go and put 2 over 3 times L in for the wavelength, we can actually tidy this fraction up again in that nice simple way. So there I'm putting in the wavelength, 2/3 L. But that is a disaster in terms of algebra, having a fraction inside the fraction. So maybe it's nice to multiply everything by 3, top and bottom. And I can end up with 3 V over 2L. But remember, V over 2L is actually the fundamental. And this is going to be triple the fundamental. So we've got a note that's 3 times as high in terms of frequency as the original note that fits on the string. Now, in the world of band, if you actually go 3 times the frequency of an original note, you will be an octave and a fifth above. And it's a very musical sound. It just kind of fits right in with the various notes that you can create in this guitar string. So those are your standing waves on a guitar. Let's go and see if we can try this out with a bit of an example. Remember, we can calculate velocity on a guitar string by going tension and dividing by the linear density, the kilograms per meter for the string. Okay, so here's the example that's in your notes. It's going to be a lot of work to get this figured out, but I think we can do it. It says you want to play a C on a guitar, which is a frequency of 131 hertz, and you want to just play it as a first harmonic, so you can take your thumb and just plain old pluck it. The string length on this guitar, actually the one I'm going to demonstrate in my classroom, is exactly a meter long. A little longer than your average guitar, actually. The line density, I took the string off and I weighed it. It was longer than a meter because I needed room on the end to tie the knots. And it was 1.31 meters long and it was 1.05 grams. Okay, we're going to see what kind of physics has to happen in order to get this to work. Right now I know the length of the part that I'm going to play. It's going to be 1 meter long. I don't know the velocity yet. Haven't calculated that line density yet. We'll get there. And I really don't know how tight this string needs to be. Okay, but we do know the mass is 1.05 grams for 1.31 meters of it. All right. Let's go to the equation for frequency that was right from your table for the first harmonic, because it did say we're going to play it just as a first harmonic. So frequency is V over 2L for that first harmonic, and I want 131 hertz. And with just a simple little bit of grade 9 math, I can see that we need a velocity of 262 meters per second. It's going to have to be fast. Okay, what do we got to do in terms of tension to get it up to a speed of 262? Well, to find that, I first need this linear density, where I take the kilograms and I'm going to divide by the meters of length for the string. Now remember, my string was a little bit more than a meter long, so I could tie the ends. And I got this incredibly tiny value for the linear density, 0.0008 kilograms per meter. Okay, we're so close. Now we can go and use this equation to find out exactly how tight that guitar string needs to be, and it is gonna be tight. We're shooting for 262 for the velocity, and we're looking for the tension. You can see I've squared both sides, so I'm going to square this, make it V squared, and I'm going to square this side to make the root go away. And what I can see is that I'm going to need 55 newtons of tension in order to get this string to be resonating at just the right note. Now, just for fun, I wanted to see how much mass, if you're wondering, what is this M that's showing up? I wanted to see how much mass you'd have to hang on the end of the guitar string just to make that kind of tension. Because, you know, you can say 55 newtons, but I'm trying to get a feeling for, like, what is that in terms of, you know, just hanging something on a guitar string. And I found that just in terms of gravity weight, if you were to use a mass that was 5.61 kilograms, I mean, that's a big cat, right? If you took a big sized cat and humanely harnessed them, of course, and used them as some weight to pull down on this guitar string, that's how tight that one guitar string has to be. So those guitar strings are awfully tight. Now, the story we've been doing here is the first of 3 cases for standing waves. It's the case where the guitar string was fixed on the ends, right? We weren't letting the ends wiggle at all. So on a guitar, you'd have the bridge and you'd have the nut holding those tight. And they're fixed. Now we're going to look at a few other options in there. But I want to move away from the guitar. I think we've talked about the guitar enough. So instead of talking about waves that are traveling as little side-to-side S waves down a guitar string, I want to talk about maybe making some waves inside a little tube, little waves of air. And that's what trumpets and trombones and saxophones and clarinets all do. So we're going to look at some air waves now inside a tube. So this next picture is going to be how a clarinet or some organ pipes actually work. And it's going to be fixed on one end and free on the other. And I've got this little picture here. You're going to see my little animation of it in a minute. And you can kind of recognize where the clarinet is in the story, but then there's all these little like blue ping pong balls, right? And you're looking at it going, what is going on? Well, those ping pong balls are going to be representing air molecules, and they're going to be like squishing each other and stretching each other out, causing a little push-pull sound wave that's happening inside the clarinet. Now down below, there's this red thing that looks like an elastic. There is no red elastic hiding inside a clarinet. The red graph is just graphing how much the little ping pong balls are moving left and right compared to their original position. So for the picture on the right, you'll notice that this ping pong ball seems to have moved from its original position. It's moved over. And the amount that it's moved over is being graphed right here as an upward amount. So maybe this ping pong ball has only moved over a little bit compared to where it was before. And so the graph has not moved up as much. But this ping pong ball here hasn't moved at all, and that's why the graph is just sitting there. So the red graph is, should I say a metaphor? It's a record of how much the air molecules are, non-technical term here, waggling left to right. So there's a lot of wagglage going on, especially in some spots on the clarinet, and the red graph is just keeping track of how much lateral movement there is, even though the red graph is being graphed up and down. Okay, let's look at a little animation of this so you can see what this looks like. So here, oh, that's not the right one, that's a trombone. There's a clarinet. This is what it looks like for the simplest possible case for a clarinet. This is the first harmonic. And what you'll notice is the air molecules at the person's mouth are not moving, for the most part because their face is in the way. But at the bell of the instrument, the air can waggle in and out. Much like a speaker diaphragm can create music, that's what's going on here. You're actually seeing this whole chain of air molecules operate in this standing wave, a little push-pull wave. And the red graph down below is recording at any moment how much those ping pong balls have waggled, non-technical term, left to right. So that is the simplest possible case, and it's going to be fixed on this side, or we might say closed if you think about it as a pipe, and then open or free on this side, right, where the air can waggle in and out so the audience can hear it. So this is the fixed free or closed open resonator, closed open standing wave. And what you can see with this lowest possible frequency, like if you look at it right there, look at that red graph, you're only seeing a quarter of a full standing wave. So if we call the length of the instrument L, then for this particular note, the standing wave is actually 4 L's long. And that's not the only standing wave that can actually be operated inside the clarinet. With a little musical magic, you can actually get this to happen. So this is the next harmonic up that works. And I say it that way because we don't call it the second harmonic, even though it's the next one to work past the first. Based on the patterning of the frequencies, it's much more desirable to call this one the third harmonic. Turns out it's going to have 3 times the frequency of the first. Take a look at this air molecule right there. It's not moving at all. There's actually waves going by, push-pull, left-right waves going by, but as they go by, they always go by in a way where the waves cancel, so that air molecule doesn't move at all. So we have a node in the clarinet right there. But the molecules here, oh, they're wiggling like crazy, and that's what this graph is showing. And so does this last one. In fact, it wiggles in an opposite phase compared to the ones 1/3 the way along. So this particular story, it looks like for the standing wave here, it's not a full standing wave in the clarinet. We see 3/4 of one. We would need a little more room to get a full standing wave in. Now here's the 5th harmonic, what it would look like in a clarinet. Now you've got an extra note in the middle of the clarinet. Notice it's still free on the end that the audience can hear and fixed where the musician's face is. Okay, so multiple waves traveling around here, bouncing off the edges, creating that pattern. Let's go and jot some stuff down in our notes here for that. So there's the pipe. The clarinets can be expensive, but they're really just a long pipe with a little flare on the end to help match that kind of sound out to the audience. And this is going to be fixed on one side with their face and free on the other. I'm going to call the length of that pipe L, and by opening and closing the little buttons on the clarinet, you're essentially changing the length of the instrument. Okay, so there's their face, sealing it off on one side, so it's fixed there and free on the other side, or we usually would just say closed open for a pipe. And we're going to have lots of air wiggling at the audience side. There must be air wiggling at the audience side. Okay, for our table, the little picture, how does it look? Here is the first note that works. We have lots of air wiggling left to right at the bell end of the instrument right here, and no air wiggling at the musician's end. I'm just going to put a little blue dot. And this kind of brown graph hidden in the background, that's recording just how much the air molecules along the way are wiggling left to right. Now, the reason for drawing that, especially that little brown kind of metaphor of wiggling, or a record of wiggling, so I can stare at it and go, wait, look, the standing wave doesn't all fit in your clarinet that's L long. You've only got a quarter of one. So the actual standing wave would be 4 clarinets long. Now, a neat way to remember that for the pattern you're going to see is 4 over 1 times L. The frequency? Well, for these instruments, you don't have to do this. In fact, you never do this. This was for guitars only, so forget that. We're just going to go with the speed of sound, which in room temperature is 343 meters per second. So in some sense, this is going to be a lot nicer than the guitar. And we're going to say, great, let's use the wave equation, V equals lambda F, right? We're using nothing but this, swinging it around for frequency, and we're going to go V on top of the lambda. The V will be 343, and it's going to sit on top of 4 times the length of the instrument. This is the lowest possible note. I'm going to say it's 1 times VL over 4L, and it is the fundamental note for that clarinet. And again, just one more time, for the V, we're just going to go 343 because that's the wave speed for sound traveling down a pipe. The next harmonic up, we're going to call it the third. It has to have air wiggling at the audience side and no wiggling at the musician side. And so you can sneak an extra note in there now. And what you can see is the clarinet is not long enough to get a full standing wave. Oh, it's close. But a full standing wave would be like up, down, down, up to there. We need a little bit more of an instrument to get a full standing wave. We're only seeing 3/4 of it. So the actual wavelength would be 4/3 of the length of the pipe. It's longer than the length of the pipe. Now, I'm just going to put 4/3 in right here for the wavelength, and I get this awkward looking fraction V all on top of 4/3 L. Well, I'm going to multiply top and bottom by 3. And what I find is this note has that same kind of base pattern of V all over 4L, but it is triple it. So it's just kind of worth noting that if you found the original fundamental frequency, this is going to be 3 times that fundamental frequency. And the pattern continues. There are no even harmonics on these instruments, on clarinets. The next one that resonates, that rings inside the instrument is the 5th, and it has an extra node, still wiggling on the audience side. If you look at how long this instrument is, you need, just to hear in order to see a full wave, we need to see 4/5 of the instrument in order to get the standing wave. And if you play the same game, putting 4/5 of the length in where lambda is, and then saying, gosh, that looks awful with that 4/5, multiply top and bottom by 5, same pattern showing up again. And what we notice is, hey, this has 5 times the frequency of the original. And so those are the harmonics that can fit inside a clarinet, where it's a standing wave of air wiggling, and it's closed on one side and open on the other. Okay, let's look at the last scenario. Let's look at the open, which is true for flutes, trumpets, trombones, saxophones. Lots of instruments behave like this. Now, a little animation of what's going on. Okay, I'm going to go back here. I think I got him here. Yeah, so this is what it looks like inside a trombone. And if you're looking at it going, what am I looking at? Well, the blue are little air molecules that are having a little P wave battle. And the red is just a record of how much they're wiggling left to right. And if you're still looking at it and saying, that don't look like no trombone to me, let me add the little brass tube. Okay, that would be like this. Oh, it's not quite lined up with it. I don't think I'm going to be able to move it. Sorry, I changed the size on this graphic. I'm not going to be able to fix it here now. but the air is wiggling in and out of the trombone. It's wiggling out on the audience side. And you might be wondering, well, how can it wiggle in and out on the musician side? There's a little trick with the way they design the mouthpieces. The way they're kind of shaped like a cone, it mathematically creates a very interesting story, things called Bessel functions. But the long and the short of it is it behaves like it's open. Because it's trimmed down to a cone at the end, unlike the clarinet, which is just a cylinder right to the end, you fool the air into thinking that it's actually open there. And so this is the lowest possible note, wiggling at the mouthpiece side and wiggling at the audience side. If the trombone player just pitches their mouth a little bit different, then all of a sudden they can create this sound. Here now I've got the air finally wiggling inside the trombone, which is good. This one has an extra node, a second node now in the center. And my graphic seems to be kind of glitching there a little bit, but you get the idea. It's wiggling on both the audience side and on the musician side. And you can even pitch again. Trombone players will often be doing like 4th, 5th, 6th harmonics as they're playing various notes in their music. So let's see if we can actually figure out what the math is going to look like for that. Okay, remember it's open and open, free to wiggle on both sides. Okay, so I'm going to call the length of the instrument L, and that tapered mouthpiece means it's going to behave like it's open, even though technically their face is in the way. So we're going to have air wiggling at the audience side. It's also going to wiggle at the mouth side, which is kind of cool the way that can actually happen. The lowest possible note looks like this. It does have air wiggling at the musician side, but it has a node right in the center. And these push-pull waves are reflecting off of the ends and then bouncing back towards the center. And when they go by the center, they're always in opposite directions, so they're fighting each other. At any one moment, if I was to take a look at this wave, what I can see is I'm seeing just a part of a standing wave. I'm not seeing all of it, just half of it. So the deal here is that the wavelength of the actual standing wave would be 2 times the length of the instrument long. And a neat way to remember it is going to be 2 over 1 times L. Now, trying to find the frequency of the note, we're just going to use the wave equation, just using nothing but V is equal to lambda F, and then solving for F, I get V over lambda, and the same thing as with the clarinet. So nice with the V, it's just going to be 343, just the speed of sound. Okay, so this is the lowest possible note that you can play, and it's 1 times V over 2L. I'm going to call that the fundamental, the original frequency for this length of pipe that we're going to play. If the trombone player just changes their face a little bit, they can make this note happen. They have to kind of tighten their lips. Now, looking at that, we have a full standing wave in there. It goes from crest to trough to crest. This is perfect. We can just say, oh yeah, lambda is equal to L, but I'm going to call it 2 over 2 times L. And if you're looking at this going, I've seen this before, this is the exact same math that we had for the guitar. So you don't have to remember 3 independent math patterns. It turns out 2 of them are identical. So the same thing happens here as it did for the second harmonic on the guitar. We're going to end up with just V over L, but a neat way to remember that is 2V over 2L, because now I can see hiding in there this pattern, and it's just telling me that I've got twice the fundamental frequency. And the pattern continues. If the trombone player or trumpet player changes their face just a little bit, or on a saxophone, there's a little key you can press to kick all the notes up, a whole set. If we change this story to the third harmonic, we're going to end up with a standing wave starting here and finishing there. We don't need the full length of the instrument. In fact, only 2/3 of it. So the wavelength for the standing wave for this note is 2/3 the length of the instrument. Now I'm going to put that 2/3 L in for lambda, and it makes that ugly mess. But if I multiply top and bottom by 3, then I can write that as 3 times V all over 2L. And I'm just, in red, I'm trying to emphasize that, hey, look, it's the same pattern we saw here, V all over 2L, except by now it's triple it. And so we've got 3 times the fundamental. And if you were to change your face again, you can get to the 4th harmonic, which is double the original one, which is actually 2 octaves up from the original note that you can get. And you can just keep changing the tightness of your lips on a trumpet or a trombone and just get to higher and higher harmonics. The same thing is true on a flute. If you kind of overblow it, you can end up getting the higher harmonics coming out as well. So that works as long as you know what the length of the instrument is. Now for a trombone player, you've seen them play, they can actually extend the slide and just lengthen the tube. And for a trumpet player, they can actually push down the valves, which plumbs in extra pipe, and they can make it longer, just like a trombone player extends the slide. The saxophone player, by opening up the holes, effectively makes the instrument shorter. So in any way you do it, and even the flute player as well, you can make the flute shorter by opening up some early holes. These musicians have an opportunity to change the length of the instrument. So not only can they change the L, but they can change their face to change the harmonics. So they've got a few different tricks they can change, that they can do to change the note that they're playing. Let's try this out just with one last example here to see if we can find how a trombone player can try to play a fairly high E, which is up at around 330 hertz. They have what they call slide positions, just kind of memorized locations for their hand as they're lengthening the trombone. All the way as close, as tight, as small as they can make it is slide position 1, and a full extension of their arm is 7. And they have a couple of little landmarks on the instrument along the way that they can use to think about which position they're in. And it's just kind of all by feel and by sound. But those are the 7 positions that they play frequently, especially probably the first 6 are probably the most commonly ones played. But they can change the length of the instrument and hit any one of those 7 lengths. And they're going to try to play this 330 hertz. So as a trumpet player or a trombone player, it's a bit of a challenge because it turns out you have to not only pick the right slide position, but then you have to pick the right face position with your lips, the right tightness of your lips in order to get the right harmonic. So they're always doing a 2-dimensional search, trying to get 2 things right at once just to get one note coming out. So let's see what it would take in order to get this 330 hertz. I'm wondering whether they can do it in position 1. So let's just try using a pipe that's 2.94 meters long. What if that's all they had? What I would do, if I was trying to do this mathematically and not as a musician, is I would just find the first harmonic for that particular length. It's probably not going to be the right note, but it's a good starting point. And so if I just go V over 2L, I'm going to go 343 for the velocity of sound, and then that original long length there, 2.94. We can make it longer later, but we'll start with 2.94. And I find that the frequency is 58 hertz, a really deep low note. No, that's not 330. But thinking back to the table, the second harmonic for that length of tube would be double it. The third harmonic would be triple. The fourth harmonic multiplied by 4. So while I'm here and looking at this 58 hertz, I'm going to catch all the other harmonics with this length and see if it could work. Second harmonic would be double that, 117. Oh, that's not right. Third harmonic, 175. No, that won't work. So they changed their face a little more. Fourth harmonic, 233. No. Fifth harmonic, 292. No, but we're getting close. Sixth harmonic, we missed it, 350. So they cannot play an E, 330 hertz, in position 1. So try a new position. You got 6 more. Don't worry, we're not going to need all 6. But you try another position. You're like, okay, we missed the 330 here. We went from 292 to 350. Let's try position 2. So now you go with a length of 312. So position 2, they extend the slide a few centimeters. It's kind of it's like halfway to where the bell of the instrument is. And they would try out that lowest note, 55 hertz. Okay, even lower than that original 58. Second harmonic, double it. Third harmonic, triple it. Fourth harmonic, multiplied by 4, I should say, from the original. Fifth harmonic, 55 times 5. Okay, moment of truth. There it is. You can play that E right there. So if you were to go and extend the length of the trombone to that length, 3.12 meters long, and then pucker your lips up to the point where you can get the sixth harmonic to come out, then you'll actually be playing the E. And so that's been kind of our little tour of standing waves. And remember, it is all about waves reflecting off the ends of the instrument. It could be a fixed end like a guitar string, or an open end like the open side of a trombone or a saxophone, and then interfering with each other on the way by. And you end up with these waves that stand in place and have very, very specific frequencies to them. And that's how most of the musical instruments work.